Hi, this is Devaragwe. I am studying in Institute of Aeronautical Engineering. I am studying BTech first year Computer Science Engineering. Today we are going to discuss about superconducting DC generators and motors. According to the technology update, the superconducting technology, that is the technology of integrated circuits, are in the second generation 100 GHz. As many other rotating electrical devices or machines, the superconducting generators are also exposed to Debye fields that could be from wide variety of sources. Superconducting DC motors. Superconducting motors are new types of AC synchronous motors. Superconducting motors are new types of AC synchronous motors that could employ high standard temperature that could employ high standard temperature superconducting windings in place of copper conventional coils. Okay, today we are going to discuss these seven topics. Introduction, 3 to 4 page. Introduction, simple DC generator, operation of simple DC generator, transfer current, stored energy, losses, and conclusion. Introduction, 3 to 4 pages. Simple DC generator, 5 to 7 pages. Operation, 8 to 9 pages. Transfer current, 10th page. Stored energy, 11th page. Losses, 12th, 13th page. Conclusion, 14th page. Introduction. Most of today's superconducting DC generators are designed for energizing large superconducting electromagnet systems, for energizing multiple constant coil magnets by simple pumps, and for energizing turning magnets by system having adjustable tuning control. The chief advantage of DC generator is the avoidance of large input sleep that would be required to carry heavy currents from external sources to superconducting devices. Because these leads can produce high heat losses, the problem becomes more significant. As superconducting wires have higher current carrying capacities are developed, superconducting DC generators or motors they will carry higher current so that it may become more loss. Another potential application of superconductivity, where the input lead heating problem is critical, is in the input and output devices required for superconducting power transmission systems. At present, it is thought that because of AC losses that have been measured in superconductors, these transmission systems must be of the DC type, even if the affects thermal condition and joule heating in the lead wire minimized. And if a heat exchange with an evaporating refrigerant were used, a direct input would place a very large demand on the refrigerating system. Now, an alternative technique is use of a transformer with a room temperature primary winding and thermally insulated from superconducting secondary winding. Okay, followed by a superconducting rectifier. However, in order for high back resistance to be obtained, high normal state resistance and large surface area are required, and thus practical efficiencies are potentially poor. Another method for avoiding the input led problems is to generate the direct current at low temperature by use of superconducting DC generator. The torque input would be supplied by means of a thin valve large diameter tube rather than a rod with a larger cross-sectional area that would be required for the same torque. This geometric factor gives an additional degree of freedom with which to minimize input-led heat leak. Alternatively, lower overall losses might result if the input were produced electromagnetically by a motor having a room temperature stator and a thermally insulated low temperature rotor. The DC generator also could be reversed and used as a motor at the transmission line termination to extract the energy. To extract the energy, the DC generator can be used as DC motor. Simple DC generator. Figure 1 shows as a simple DC generator consisting of a sheet of low critical field superconductor such as lead, to which it is connected with a loop of high field superconductor material such as niobium tin. It was necessary to develop special techniques for making the superconducting joints. A permanent magnet rotates about an axis so that its path tra- its path traverses its path traverses the lead it path traverses the lead sheet as shown. Its distance from the shape, its pole shape, and its strength are adjusted in such a way that. Okay, figure 1 shows a plan view of simple DC generator. First, it is with a high field superconductor neodymium tin loop at the top. Next, superconducting joints are made. Normal spot, permanent magnet. Normal spot is just for spotting. low field superconducting lead sheet is covered by the okay. Permanent magnet is covered by the low field superconducting lead sheet. Axis of rotation. From that axis, it rotation, and this is the path of magnet where magnet will rotate. Figure 2 shows the detailing of superconducting sheet. Moment, normal spot, fixed element. Figure 3 equivalent circuit. Figure 3 shows this equivalent circuit for inducing persistent current, showing the essential elements schematically. That's equivalent circuit. Normal spot will be produced in the superconducting sheet by exceeding the critical magnetic field at the operating temperature. This spot is penetrable by magnetic flux, whereas the remainder of the superconducting sheet is perfectly diamagnetic and expels magnetic flux. As the magnet is rotated counterclockwise, a normal spot of materials forms at the edge of the superconducting sheet and is drawn across the sheet by a magnet. That is, magnetic flux is trapped in the normal spot and taken across the sheet. This flux is surrounded by a closed superconducting loop consisting of the lead plate and niobium wire, and thus a persistent current is induced in the circuit. As the magnet completes the cycle, it crosses the niobium tin wire. However, it is not switched normally because of the high critical field of niobium tin wire. If the magnet is kept at a constant distance from the lead sheet, there are virtually no circulating currents around the spot despite the flux trap in it, since the magnetic field is maintained by the permanent magnet. With each cycle, more flux is taken into the superconducting loop, a higher persistent current is induced, and more magnetic energy derived from the torque required to turn the magnet is stored. The limit is reached when the critical current for the neodymium plate or the self-induced critical field of the lead sheet is attained. This current may be several hundred amperes. The current may be huge. There is then either a saturation effect. Saturation effect is a limiting current being reached. Saturation effect is the maximum current that can be reached in the circuit, or a complete temporary transition to the normal state at some point in the circuit, so that all flux leaks out and the persistent current is dissipated. It's the equation of current. The magnitude of induced persistent current is given by the classical equation I equal to phi by L. Where phi is the total flux trapped in the circuit and L is the inductance of the closed circuit. I is equal to phi by L is basic equation we derived. This is the first equation derived in this video. Operation of simple DC generator. Let us now consider the means for inducing the persistent current. Figure 2 shows fixed resistor element as the normal spot. As a normal spot is smooth flux crosses the element. A Faraday induction voltage is produced across it, and a counterflow current is produced. A complex return path is provided by other elements, including the remainder of the lead plate, which is superconducting but still has inductance, and the niobium tin loop. The adhesion elements are shown in figure 3 and 4. Figure 3 and figure 4. The work done by the torque that turns the magnet compresses magnetic flux into a higher field energy region. The torque is proportional to the speed and so is Faraday electromotive force generating the persistent current. If the magnet is stopped, the EMF is removed and the persistent current remains at the constant value. Note that the persistent current is being altered by the Faraday induced current. All the time magnet is crossed the sheet and there are no large edges wedging effects. Although the flux trapped with the loop changes discontinuously, so does the total loop inductance, and a smooth variation of currents is therefore produced. In the calculation of energy changes in the system, inductance changes are caused by the movement of the magnet must be considered as much the current changes. Work is also done when the magnet crosses the niobium tin wire. However, if we rotate the magnet without forming a normal spot in the sheet, for example, by cooling the sheet, if we rotate a magnet further so that its critical field became greater than the field produced by the magnet network, then during a complete cycle would be zero. Therefore, we need to consider only the additional work done in moving the normal spot across the lead sheet. The various circulating currents. The various circulating currents in the circuit are shown in figure 5. The persistent current is produced by the total flux enclosed in the superconducting circuits as the result of previous rotations of the magnet. Because the because the total inductance of the circuit will fluctuate while the magnet is crossing the sheet. This current will also fluctuate as the magnet traverses the magnet traverses the sheet. Lithium decreases from infinity and L2 increases. L2 is inductor to initially all the persistent current is carried in L2. Finally, L2 is inductor. Finally, it's all in L1. From L2, it will go to the L1, the current supply. The induced Faraday currents add to the currents in lithium. Okay, it's in L1. In L2, an additional transfer current from L2 to L1 as shows. Figure 4 shows the simplified version of circuit figure 3. In figure 3, there are some normal spot and something. In figure 4, there's a simplified version. It's a simplified version. This argument. Figure 5 shows circulating currents in superconducting circuit. In figure 4, the direction of current are shown by the figure 5. In figure 4, there is a battery connected resistor in series and L1, L2, L3 are three inductors connected in parallel to the circuit for cell and resistor. Okay. In figure 5, circulating currents in superconducting circuit. Direction of magnet is reverse, transferring current direction from L1, starting from L1. Okay, it's from L2 to L1. Persistent current L1 Persistent current is from cell to L3. Faraday currents are from cell to L2 to L1 to the L1. Direction of magnet traverse. The transfer current. Since it flows in purely reactive components, the transfer current shown in figure 5 is lossless. It has no loss. Thus, as the normal spot travels across the sheet, it moves into a portion that is carrying no current. Okay. If current were being carried, part of the persistent current would be dissipated in the normal spot before it was transferred to the superconducting portion. The result would be similar to the switching loss mechanism that occurs in cyclotron circuits. Because of the implication, the reasons that the persistent current should always flow around the normal spot and the current should flow around the normal spot, otherwise it will be turned as zero. Should flow around normal spot and never be forced to cross it as a normal spot is taken across the sheet is not immediately apparent. Consider therefore the following special case. The normal spot is centered in the sheet with a large persistent current in the circuit. It is then oscillated from side to side, almost but not quite reaching the edges. The persistent current, in order not to exceed the critical value, must therefore reaching the edges must therefore transfer from side to side. In uniform oscillations are made. If uniform oscillations are made and then spot is stopped in the same place once more, the net effect of Faraday currents on the persistent current will be nil. There will be, however, an irreversible dissipation in the normal spot, and work must be done in moving the magnet to overcome this energy loss. At the completion of this operation, the loop circuit inductance is the same at the start and start. And since the superconducting loop has not been broken, the total stored flux cannot have been altered. Therefore, the persistent current remains unaltered, and the transfer current, which has been altering the persistent current between L1 and L2, inductor L1 and inductor L2, must be lossless and previously supposed. Stored energy. These are some equations for energy storing. The energy stored Q per cycle is equal to half I plus delta I whole square minus I square, or L into I plus delta I by 2 into delta I whole square. This is the equation 2 derived in this video, where L is the total inductance of the circuit, I is the persistent current at the start of the cycle, and delta and the change in current. The current induced by a flux increment. The current induced by the flux will change continuously in inductor to inductor. Increment A added during the cycle. Therefore, delta I equal to delta pi by L, where delta pi we already derived. This is the first equation we derived. I equal to delta pi by L, where delta pi is the total flux, L is the equivalent inductance. Delta I is the current induced by the flux. For a small number of turns and delta phi will remain nearly constant. For a large number of turns, it will be altered by the magnetic field produced by the persistent current, adding vectorially to the field of the permanent magnet. We can therefore write delta phi equal to n delta phi, or delta I equal to n delta I equal to I by n. Equation 2 may be written as, this is the next form of equation 2. Equation 3, we have derived it first only. Q equal to delta phi whole square by L into n plus 1 by 2. The L into n plus 1 by 2 is in the denominator, and delta phi square is in the numerator. This is the equation 4. This is the next form of equation 2. Equation 2 may be written as equation 4. Both are same. This form of equation 2 is a useful approximation for calculating efficiency during startup of the DC generator. For a large number of turns, we can simplify equation 2 assuming I greater than delta I, then Q equal to I delta I. Simple. Q is also equal to I into change in flux. This approximation will be used in our calculations of operating efficiency. Losses. The energy loss in the system include mechanical losses, high frequency losses, losses in the normal spot, loss in the normal spot, and speed losses. Okay. The energy loss in the system include four types of losses. First loss, mechanical loss, such as mechanical losses such as bearing friction, viscous damping, etc. This will not be considered at present. Okay. Mechanical losses are due to the friction and viscous damping and some more. High frequency losses. Although superconductors have AC losses, we will restrict ourselves to the low frequency case at present because we are dealing with only DC direct current. Later we'll be briefly discuss about reducing losses attributed to high frequency operation. Actually, high frequency losses are to the AC generators and motors. Now we are dealing with the DC. There are no frequency losses because we are using low frequency. Losses in the normal spot due to Faraday current. The sum of these in each element may be calculated as loss can be calculated by this equation. The equation is loss equal to sigma integral of Vi dt. Vi is power loss, where T is time, I is in Faraday, T is in time, I is a Faraday current through the spot, normal spot, and V equal to E minus L di by dt. After differentiating it, it's a normal form equal to E into K L3. K L3. L3 is the third inductor di by dt, where K is geometric constant and L3 is the total inductance of the superconducting circuit as shown in figure. Next slide, we have figure. If we rotate the magnet at a constant speed, V will be constant. We will assume it to be a maximum value E. Therefore, loss equal to E into sigma of integral I dt, where V can be neglected. The equation 8 is the next form. Equation 6 can be written in the form of equation 8. V will be constant as E in the equation 8. Okay, these are in the SI units, the equations. Next, in Celsius units, Q equal to delta pi by 10 power 8 into R. R is the resistance, where Q is the charge induced on a ballistic galvanometer by removing Z coil from a magnetic field, where R is represented as previous to typical DC generator design. Rotating permanent magnet in the middle, High-field superconductors are connected to the load. There is a small gap between superconducting joints and high-field superconductors. Okay, at the end, strips superconducting joints and the normal spot where the generator moves. Low-field superconducting sheet is covered by the normal spot. Normal spot is covered by the low-field superconducting sheet. Conclusion. Large superconducting DC generators can be designed for low losses. They could serve as ideal input devices for DC superconducting power transmission lines. In reverse, that they could be used as motors to drive room temperature AC generators at the outputs. They also may be employed as input-output devices for inductive energy storage systems using superconducting electromagnetic currents. Thank you for listening with the patience.